Hello and welcome to the Unit 12 podcast on section 25.4. Today we're going to be talking about fission and fusion of nuclei, and I'm Mr. Sakaguchi.
And I am Mr. Lin.
And here we go. Nuclear reactions and energy. Mass is conserved in all chemical reactions, but this isn't true for nuclear reactions. If you remember Einstein's famous equation E equals mc squared, you can kind of understand why at this small quantum level, why mass and energy are closely related. So what happens is when energy is released, you lose a small amount of subatomic mass.
What also you should be aware of is where this energy comes from. Yes, it's from a mass conversion. This is also energy that's released when that strong nuclear force that we talked about in a previous podcast is released.
Correct. Binding energy. This is the energy needed to break 1 mole of nuclei into individual atoms. And what we find is that there's a correlation between binding energy and stable nuclei. The larger the binding energy, the more stable the nuclei is.
And the elements with a mass number of around 60 tend to be the most stable. So it's from there, and then as you can see on the diagram to the right, from a mass of 60 and then goes left and right of the diagram, the stability starts to decrease.
Yeah, so you can kind of see, like, if you have a mass over 60, you're more likely to stabilize through fission, whereas if it's less, it's more through fusion. And we'll talk more about what fission and fusion is, even though you probably already have an idea. There's also a mass defect, and this is the difference in mass between a nucleus and its component nucleons. The mass changes are associated with energy changes in nuclear reactions.
And these are really small mass changes. But you have to understand that since due to the Einstein's equation, that small mass change amounts to a large amount of energy. So for instance, when you simply lose an alpha particle down here, the mass change is very, very tiny, but the amount of energy release is pretty massive. And that's just for something that weighs far less than a gram, and you get that amount of energy.
Yeah, this is a fusion reaction.
Right.
And it's amazing how much energy you get from such a small change. One of the processes we're going to talk about is nuclear fission. Fission is breaking the nucleus into smaller fragments. Nuclear power plants use fission as a basis of creating energy, and we use neutrons as a way to initiate fission by kind of like throwing it into the nucleus to split it up.
So what you do is atoms or nuclei slam into each other, or a neutron slams into a nucleus hard enough and it causes it to split, and this splitting causes other neutrons to fly out and split and hit other nuclei, and keeps on going, and this is what's called a chain reaction. And in order for this chain reaction to maintain itself, it has to have a certain amount of mass associated with it. This is called critical mass.
Right. So nuclear reactors basically are controlled fission reactions. They contain controlled fission reactions in them. The way power plants are created is we have fuel rods, which contain uranium-235. We have control rods that absorb neutrons, and we have moderator rods that slow down neutrons. So the purpose behind the control rods is to basically prevent the fission reaction from getting out of control by absorbing neutrons and reducing the number of fission reactions that can occur. Moderator rods slow down the neutrons so that fissions can occur, because if the neutrons are moving too quickly, they'll go right through the nuclei, not split it, and actually go through the containment field, which would also be very bad.
Right. So nuclear reactors help control nuclear fission reaction. And as a result, what really happens is essentially the nuclear fuel rods are used to generate heat, and then it boils water, and that boiled water or steam is used to spin a turbine. And that turbine, as it spins, generates electricity. So essentially, we're using nuclear power to boil water to cause something to turn, and that's how we generate electricity that way.
And breeder reactors are a special kind of nuclear reactor that's used more often now, and this is basically a way to kind of recycle spent fuel rods to get a little bit more energy out of them.
Right.
We also have fusion. Fusion is the combining of nuclei, so you can kind of think of it as the opposite of fission. What's nice about fusion reactions is that they give off large amounts of energy. Our sun and any star out in the galaxy are basically giant fusion reactors.
The products from fusion reactors or fusion reactions are not radioactive because what you're doing is you're taking small nuclei, slamming them together to produce heavier nuclei, and these heavier nuclei tend to be stable. These higher energies that are produced also require more energy to start them off and to sustain. Problem with the nuclear fusion, why we don't have nuclear fusion reactors, despite the fact that they have more energy output, is that we can't control them. We have been able to initiate nuclear fusion reactions with bombs like the hydrogen bomb, but to contain it and control the speed of the reaction, we haven't found a way to do that yet.
Yeah, some of the even though the products are not radioactive either, which is also an attractive byproduct. Containing the reaction, there isn't something that can maintain that high temperature without melting out. So they've been trying to contain these fusion reactions in magnetic fields with limited success.
Right, and it does not happen like in Spider-Man 2, by the way.
Right. And then we have thermonuclear reactions, which are basically fusion reactions.
Right.
And that is it.